Okay, we'll work through the solution to quiz 9 for statics, MENG1230. So as you may recall, we have this rod that's attached with a ball and socket joint. So that ball and socket joint gives us a reaction force. Make this smaller. In Z, gives us a reaction force, or it could give us a reaction force in Y as well as in the X direction. What else do we have going on? We have these tensions from B to C. We call that tension BC, and from B to D. And we also have this load here that's being applied straight down. Maybe it's a weight, maybe it's something else that's attached to this that is being supported by this assembly. So what are the steps to solving this problem? Our first step is find the coordinates of each point. Our second step is to find our position vectors. Third step then is to find our tension BC and tension BD in their components. So we use our position vectors to do that, or our unit vectors. That flows into unit vectors. Let me put that there. And then fourth, we'll do some moments. And then fifth, we'll use equations of equilibrium to find our unknowns. Alright, so that's our plan. Let's get started. So we'll start with our coordinates. Maybe I'll zoom out just for a second so we can see the whole diagram as well as our writing area here. Let me come out one more. Alright, perfect. So our coordinates, we've got A is at 0, 0, 0. So that's right here, right at the origin. There's our A. Point B here is in the X direction, 3 meters plus 3 meters. So it's going to be 6, 0, 0. C is at 0 in X. It's on the YZ plane over here. And it's negative 2 in Y. And plus 3. There's that plus 3 in Z. D is pretty similar. It's just the opposite sign for Y. And then finally E. It's halfway along the way from A to B. So it's going to be 3, 0, 0. So we got that section done here. Now we'll do our position vectors. So we're going to have, where do we need position vectors? Well, we need position vectors from B to C and B to D, as well as we have a couple moments going on, so we need a vector from A to B as well as A to E. So we're going to find our position vectors R, B, C, R, B, D. Oh, excuse me. Yep, that's correct. B, D. So let's start with those two. So we're going to C, starting from B. So we have to take the coordinates of C, subtracting off the coordinates of B. So we're going to have 0 minus 6. So we have negative 6I plus negative 2 minus 0j, so negative 2j. And then 3 minus 0k, so plus 3k. And our units for that are meters. Similarly for BD, we'll have the same in the x direction, negative 6I. This time we're going in the y direction, plus 2, plus 2j, plus 3k meters. And then we also have, let me scroll down, we have a position vector from A to B to get our moments that we'll use there. So we're going to use the BC and BD to find our unit vectors UBC and UBD, and our tension times that unit vector will give us the force along that chord. Now we're going to need position vectors for a different purpose here. These are to use to calculate some moments. So we're going to do finding RAB, and that's pretty straightforward. That's since A is 0, 0, 0, we just take B's coordinates. So we have 6I meters, and RAE equals 3I meters. So we've got our position vectors. We'll need some unit vectors for RB and RBC and RBD. So our coordinates for that, so just the magnitude of that vector is going to be the square root of 6 squared plus 2 squared plus 3 squared. And I dropped the negative sign since we're squaring it. And so we have 36 plus 4 gets us 40, plus 3 squared is 49. So RBC equals the square root of 49, which is 7. And we've got the same thing here for BD, right? 36 plus 4 plus 9 is 49. So RBD equals 7 as well. So let me scroll down a little bit. So I'm going to call this, I'll call this step 2B unit vectors. So we're going to have UBC equals negative 6 sevenths I minus 2 sevenths J plus 3 sevenths K. So I just took this position vector and divided by this magnitude. Similarly, UBD equals negative 6 sevenths I plus 2 sevenths J plus 3 sevenths K. And I'll get you a point for that and a point for that. So we have our unit vectors. So that's done. Now we need to find our tension BC and BD in components. So 3, I'm going to call it FBC equals our tension in BC times that vector, right? So we're going to have negative 6 sevenths I minus 2 sevenths J plus 3 sevenths K. And that will get us now units of newtons. So our unit vector is unitless. Our position vector had units of meters. So when we have that unitless, we're multiplying by this here that has units of, that tension has units of newtons. So we have units of newtons for this force. And then FBD equals our tension BD times our negative 6 sevenths I plus 2 sevenths J plus 3 sevenths K, and that's units of newtons as well. Alright, so we got step 3 done. Now onto the moments. So we can calculate, we have 3 places where moments are acting on this, or actually we have 3 moments, 2 places where they're acting. So we have moments that are being applied, the forces are being applied at B, and we're going to be finding a moment around A, and then we also have another place here at E where that force is being applied down and creating a moment around A. So we have 2 options for these tensions here, BC and BD. We could take tension BC, we could cross that with this position vector. So this position vector RAB cross with force BC, that gets us our moment around A due to BC. And then we could do that again, that position vector RAB crossed with the force BD, and that gets us our moment from BD around A. Or, since they're acting at the same point, we can add these forces together, get a resultant force. Or that resultant force be acting? Well, that resultant force would be acting something like this. We don't know for certain, but we could figure that out. So we'd have our our tension BC times our I component plus our tension BD times our I component. That quantity in our force line of our cross product. So we could do that. We could do the other way. It's our choice here. I'm going to do it separately at this point. Maybe in the future we can combine those together. We talk about that in class and show that. And then this other force down here is going to have a moment. It's acting at a different location, so we can't combine that with these forces because it's crossed with a different position vector. All right, so let's start with the moment from BD, or BC, excuse me. So 4 moments. And I might be able to squeeze this in at the bottom of this page, or I might have to slide over to the other half here. So the moment around A due to force BC equals, where's our cross product? I, J, K. What's our position vector? So this is where our RAB comes in. That's 6, 0, 0. And our force BC is up here. It's going to be -6/7 tension BC minus 2/7 tension BC times 3/7 tension BC and K. Alright, and I'm going to add my other my first column over again here, 6 and -6/7 tension BC. Alright, so we'll take our cross product. So we'll cover up the I column and row. So we have 0 times 3/7 tension BC minus 0 times -2/7 BC. So we get 0I plus, what do we have in J? We're going to have 0 times this minus 6 times 3/7. So we're going to have -18/7 tension BC in the J direction. And then in K, we're going to have 6 times -2/7 tension BC minus 0. So we're going to get -12/7 tension BC in K. So that's our moment in around A due to the force BC. And then we'll take another moment up here, moment around A due to the force BD. So this is very similar. It's going to be I, J, K. And our position vector again is RAB. So that's 6, 0, 0. And our force BD equals -6/7 tension BD plus 2/7 tension BD. And then 3/7 tension BD. And then copying that first column over again, I6, -6/7 tension BD. Alright, so here we go. So we're get our I again, it's going to be 0, 0I, J, we're going to have 0 times that, minus 18/7 tension BD, and that's J. And K, we're going to have 6 times 2/7, it's going to be 12/7 minus 0 plus 12/7 tension BD. And that's the force around acting at BD. And then finally, we can probably just visualize this last one. We have 3 meters times our 600 newtons. I'm putting up my hand here, imagine that. So my fingers are pointing towards the x-axis in the direction of AE, curling towards the -z direction, and my thumb is pointing in the positive y direction. So that's going to give me a moment in the positive j direction. So I'm going to have 3 meters times 600 newtons. So my moment around A due to the force at E equals 600 newtons, and that's multiplied by 3 meters, and that's all going to be in J. So that equals 1800 Newton meters in J. So there we go. There's our moments. And then now we can use our equations of equilibrium. So you get a point for each of these moments. I should write that down here. So there's a +1 here, a +1 here. a +1 here. So we've got half of our points so far. Now we can finally use our equations of equilibrium. So let me scroll down just a tad more and we'll start this off. So step 5, equations of equilibrium. Okay, so we're going to have the sum of the moments around A have to add up to be 0, right? There's no moment at A, so we can't end up with some moment there. It's just a pin, a ball and socket. So we have 3 reaction forces but no moment. So what are those moments? We'll add those up. So I've got my BC over here, our BD over here, and my FE over there. So we're going to have 0I plus 0I plus 0I. So we're going to have 0I, and then we're going to have -18 sevenths BC minus 18 sevenths BD and 1800 J. Those are all J. So we're going to have plus -18 over 7 tension BC minus 18 over 7 tension BD plus 1800 in J. And then in K, we're going to have, what do we have? We have -12 sevenths tension BC plus 12 sevenths tension BD and nothing. So we're going to have plus, I'm just going to flip those around. No, I'll keep it the same. So -12 sevenths tension BC plus 12 sevenths tension BD in K. Alright, so now I can scroll down a little bit more and give us some room. So if the sum of these moments is 0, that means that our I components equal 0, our J components equal 0, and our K components equal 0. So I'm going to start with my K components here. So K components. So we have -12 sevenths tension BC plus 12 sevenths tension BD equals 0. So 12 sevenths tension BD equals 12 sevenths tension BC. So TBC equals tension BD. Alright, so we can use that in our other equations here. So then I'll rewrite this J component section. So we're going to have -18 sevenths, and I'll just call everything tension BC here since tension BC and BD are equal, minus 18 sevenths tension BC plus 1800 equals 0. So let me scroll that down a little bit. So I'm going to have, I'm going to keep my 1800 on that side and move my -36 sevenths to the other side. So I'll get 36 sevenths tension BC. So tension BC equals, I believe it's 350. Is that right? Yep. Equals 350 newtons. And then also because tension BC equals tension BD equals 350 newtons. So you get +1 here and +1 here. And now we can do our equilibrium in X and Y forces. So here, well, sum of the forces X to equal 0. So what are X forces again? Let me scroll up. I've got it on my notes here as well, but my X forces, so I'll have -6 sevenths tension BC plus -6 sevenths tension BD. What else is acting in X? I only have this reaction force. This is all in Z, and these are in X and X. So only the reaction and those other two forces there. So let me come down. So we have -6 sevenths times 350 newtons plus -6 sevenths times 350 newtons plus a reaction force at reaction force at A in the X direction equals 0. So FAX equals 12 sevenths times 350 newtons and that equals 600 newtons. FAX 600 newtons. So we get a point for that. Sum of the forces in y equals 0. So what do we have in the y direction? Well, for BC we have -2/7 times 350. For BD we have +2/7 times 350. And then we have our y reaction force at A equals 0. So these two cancel each other out, so FAY equals 0. So you get a point for that. And then our last point, sum of the forces in Z equaling 0. So what do we have there? We have equals 3/7 times 350. Let me put a newton down here just to be clear. Plus 3/7 times 350 minus 600, and then plus FAZ. So what do we get there? We get 6/7 times 350 minus 600 FAZ. That all equals 0. So I can subtract that off to the other side there. So FAZ equals 300 newtons. So we get 600 on that side is plus 600. This is 350 divided by 7 is 50 times 6, negative 300 on when we move it over to this side, so we get 300 newtons. That's our last point there. So we get +1 there. So we get 1, 2, 3, our 2 tensions, 4, 5, our 3 moments, 6, 7, 8, and then our 2 unit vectors, 9, 10 points. So I hope that makes a little more sense when we walk through that quiz problem. We can answer any other questions you have in class or in office hours.